Hello, good evening, and welcome to Average Expectations. Today we're going to have a bit of a shorter stream because I've got a number of things coming up, including some relatives for Thanksgiving in Canada. So let's jump into everything. Quick talk about the channel, Average Expectations. We do programming and we do lots of other things that are not programming, but somehow you can convince a computer to do those things. I stream every Friday, except last Friday, starting at 8 p.m. in Eastern Time. Basic rules in chat is basically don't harass anyone, don't spam, and don't give out personal information. If you're here for unofficial office hours and you have something that's a really specific personal question, direct that through the other channels of the course. But you can ping me to take a look at that early. I expect next week will be busier because there'll be the due date for problem set 2. So without further ado, let's go over the projects. So far, I tested my Leonard Cohen deepfake. That was my test stream. We did kind of finish the first project that I wanted to do, which was 12-tone music. And that was fun. It didn't work quite as well as I hoped, and I did not get to fixing and adding all the features I wanted. But nevertheless, it was a finished project, more or less. So maybe I'll revisit that in the future. But for now, we've got bigger fish to fry because I've got a project that's related to some other things I'm doing, which is to create this kind of piano synthesizer. And I'm going to explain more about how that works today because that's the project I'm setting up now. And then after that, very exciting, is I'm going to try combining Dwarf Fortress, which is a video game, with Stable Diffusion, which is an image generating AI. So that's kind of in the future. But for now, let's jump into this talking piano thing. So on to our favorite thing, which is the slide deck. It seems like everyone in academia and industry loves to present everything through slides. I don't know why, but I'm not questioning it. So today is the singing piano. And the reason why I call it the singing piano is because, there's a talking piano out there. In fact, there's a pretty famous video, if you look on YouTube, by Mark Rober, I think. And he basically makes a piano talk. So it's called a talking piano because it sounds like somebody talking. And I'm going to go over roughly how that works on today's menu. I'm going to go over some of the basics and we're just going to set things up because next week I'll actually try to build something. This week will mostly be just like explaining the background and trying to get something working, which basically means stealing somebody else's code and running it as if we did it ourselves. That's a classic computer science thing to do. You know, I just heard a computer science professor from Stanford talking about this on YouTube. And so if they say that it's okay to steal other people's code on GitHub, then you heard it from the authorities. So I guess we can do the same thing. So on today's menu, I'm gonna try to explain a little bit about overtones, and then the whole idea of music synthesis, and then link that up with some totally unrelated math, which I won't explain beyond like, here's some hand waving things that try to say this works without actually saying how it works too much. And then we'll get some code and try to turn it into some MIDI, which sounds like a talking piano. So without further ado, overtones. So what are overtones? Well, when you make any kind of wave, and sound is just a wave, right? You can actually get some interesting effects going. So I'm going to make a wave. I'm going to draw a wave here. It's going to look like this. Oh, hey, that's a pretty nice wave. So, okay, that's enough wave for now. So you can see this is a wave, and it's not really a sound wave because real sound waves are pressure waves. That means that they squeeze and expand the air. And this is more like an ocean wave. An ocean wave goes up and down against the pull of gravity, right? So obviously those things aren't alike, but you can kind of represent them the same way. And the way you imagine it is, imagine the peak here of the wave is like the how would I describe it? Like the high pressure point in the sound, and then the valley is the low pressure point. And as you move in time, imagine moving from left to right. So you're standing still, but time is moving forward, and as you move forward along this thing, you'll see that the pressure increases, so you feel a squeeze, and then later the pressure decreases, so you feel a stretch. And it's that squeeze and stretch which makes sound a thing. And so now that's the basic idea behind sound. And of course you can measure a very important part of this this sound thing, which is the wavelength. And so if you measure, let's say, from the peak of this trough to the next peak, and if I can draw a straight line here, then what you have here is what we call, what we call a wavelength, right? So you can see that's from one peak to another, and we're going to give it a name, right? And why is that dark? That's weird. Okay, I don't want it dark. There, that's better. Okay, so that's a wavelength without the one, and the wavelength controls how you hear that sound. Specifically, the shorter the wavelength, the faster the frequency, and then the higher pitch you perceive that, right? So big wavelength is low sound, small wavelength is fast sound, you could say, high pitch sound. So here's the tricky thing though. When you make a sound, let's say, here's a couple ways to do it, right? Imagine you've got a string and I pluck it, then that string is going to look something like this. Oops. Let's make another drawing, right? So now I've got, so the previous one was sound. What is a sound? Right, and we'll just move this down a bit. Okay, overtones. So what's an overtone? Well, let's edit this wave a bit. Imagine now that you're plucking a string to make this wave, right? So, oops, that's too much editing. So what that might look like is you pluck it in the middle, and the two ends are kind of attached to something, so they can't move, right? So that wave is going to bounce up and down from where you plucked it. So I'm just going to draw two halves to this, and I'm going to flip one of them. Range, rotate. Yeah, oops, not horizontal, vertical. So it's flipping from the first position to the second. Let's give it a different color, right? So it's going from yellow to orange and back. Let's give it a more different color, level yellow to blue. Okay, so you can see it's going like this, right? And so that's the fundamental frequency of this string. That's the biggest wavelength that fits. Actually, it's half a wavelength, because you can see there's only one peak here. There's not two peaks. So that's the lowest sound you can get from plucking this string. But that's not the only sound you can get, because we could also fit two waves in here. And if I do that, let's make another copy of this. I'm just gonna take this guy and I'm gonna like cut it in half and fit two of them like this. Well, if we go back and forth, you can see that they fit in the same space, right? This string is the same length either way. But in this diagram, you can see that I've actually created two of these waves, right? So I should actually flip these. So you can see that this string can actually vibrate in two different modes, and we call this mode, where it's got two humps instead of one, the first overtone of the string. And you can actually do this again. Like, I'm just gonna copy it out, right? Shrink it down, and guess what? It just so happens that oops, that's probably too much. It should be about here, because it just so happens that you could fit exactly 3 of these strings together, or these humps together. So now you have a second overtone, and in this case you have 3 humps, 3 half waves. So if we go back to the beginning, this was half a wavelength. Now we have 1 wavelength, and then 1.5 wavelengths, and the ratios are, if this is 1, this would be 2, and then this would be 3, right? So you can see that every overtone that fits into this length of string has to divide the string evenly. And so if, for example, let's create one that's kind of in the middle, right? We'll go in the middle of the first one and the second one. So if I try this, I'll resize it first, and I'll try to fit another one in. And this one's like just a little too long to fit in, right? You can see this was the original length, and it goes to here. And you can clearly see this part is not going to fit inside the length of the string. And that's important because remember, the string is held on both ends. Let's add a little shape to show that, like a little circle. Yeah. Dark blue. No border. Okay. I don't like dark blue. Let's just go white. Okay. So if I take this, I'm gonna stick these little stoppers at each end of the string just to show you the string can't move on either end, right? So you can see at every one of these overtones, the string is still not moving at either end, so it's totally fine. But here, if I try to do this, you can see this doesn't work, right? So let's put a big fat X around that to show that. Doesn't work. Okay, so the point of all this is that the string can't just vibrate however it likes, right? You can see in this case, it doesn't fit. However, anytime there's an integer number or like, a nice even division of the string into equal size parts, then you can get an overtone. And so that's the basic idea behind sound, is that when you make something vibrate, you don't just get one frequency out of it. You can actually get a whole bunch, and there are all these related overtones. And you can fit as many as you can possibly do. Like you can have 4 of these, you can have 5 of these, you can have 10, you can have 20, right? It's just they will have different amounts of energy depending on how you pluck the string. So let's go into that. If I copy this one out again, this one has just 1/2 of a wavelength, right? Imagine if I pluck it in the middle. It's going to make it pretty hard to go into this mode here, right? Because here you'll notice the middle is also stopped, right? It looks like this, right? So if I try to pluck it like this, that's clearly not going to work, right? Because the middle is going to move. And so the way these overtones sound actually depends on the way the string is plucked. And actually there's a really cool demonstration of this on YouTube for 2-dimensional shapes, which are like plates. If you try to make a plate vibrate, it will create these really cool patterns, which you can also see on the opening of the new Lord of the Rings series on Amazon. So yeah, I'm not getting paid to shill any of this. I don't know why I'm talking about it. But the point is that these overtones can create really interesting effects. So what does that have to do with music? Well, the next thing on our menu is synths. So let's go into that. And we'll find a nice picture of a synth. Yeah, okay, this looks pretty cool, right? Oops. Okay, just copy the image. Yeah, okay, there's a synth. Right. Actually, it's not that kind of synth. This is the extent of academic humor, right? It's just making stupid puns on things. But that's fine, because I like puns. Oops. Okay, so the thing on the right is a music synth. The thing on the left is a science fiction synth. And what we're talking about here is trying to create sounds that sound like real instruments, but without the real instrument involved. So you might wonder how you can do that. Well, it turns out different things sound different, not just because they have different pitches or loudnesses, but also because of their overtone content. So the way I would describe this is let's imagine you have a flute. Okay, so a flute might have, if I copy this over, flute might have a lot of this. Oh, we gotta resize these. These are huge. Yeah, okay, that's better. Okay, flute might have a lot of this, and then maybe like a lot of this. Okay, so that's a flute. Well, on the other hand, maybe we have a clarinet. I used to play the clarinet, so we gotta go there. And maybe the clarinet has like, I'm making this up, by the way. Like I don't think the actual instruments have exactly these overtones, but I'm gonna make it up anyway. This is just a demonstration. It's not the reality, right? We'll get to the reality pretty soon. So what I'm showing you here is both of these instruments are playing the same note, so they have the same frequency, which is this first row, right? But the second row shows maybe what their overtones are, and the flute tends to have a lot more of the first overtone, whereas the clarinet has more of the second. It skips over one overtone generally. And the reason for this is kind of more rooted in acoustics. The way it works is that the clarinet is like, basically it's got a really narrow tube, so one end is kind of constrained. Yeah. So on the reed end of the clarinet, it vibrates a lot. But on the other end, because it's got a narrow tube going into like the open air, it's almost like there's a stop there, which prevents the air from vibrating. The technical term for this is impedance. There's an impedance mismatch between the exterior air and the inside of the clarinet. So the clarinet has this effect, the flute has a different effect. They have the same tone in this case, but they have different overtones. So your ear can pick that up, and it hears a flute as one thing and a clarinet as another thing, even when they're playing the exact same note. So that's the basic principle that we're going to exploit when we design a synth. So when we use a synth, what we're really doing is we're taking this note and we're applying a bunch of numbers to it. So we have some fundamental frequency. Let's say it's A, because A is 440, right? That's kind of the music standard in this world nowadays. Not in the past, but nowadays, the standard for an A note in the middle of the piano is 440. So we'll say this is 440 hertz. Okay. And on this side, it's the same because it's also playing the same note, right? But for the notes, for the overtones on top of that, the synth is going to play a little bit of the next overtone, which is double this, which is 880 hertz. And over here, it's gonna not play that, right? Because the clarinet does not have that overtone. And finally, the last overtone was 3 times this, so we need to multiply 440 by 3, which is 12, 13, 20. Okay, so that's the basic principle here, right? And now, in addition to the frequency, you can imagine we have a loudness value associated with each of these. So let's say this is like a loudness of 10. No, let's think MIDI, because we're going to use MIDI later today. So let's say this is a volume of 80, right? These are totally arbitrary numbers, but the point is we're going to play a tone of 440 hertz at a loudness of 80, but then on top of that, we're also going to play a quieter tone up here, which is for the first overtone of the flute, and let's say this is like 40, right? And then just dot my I's and cross my T's. Loudness. So we have 2 kinds of loudness, right? Same loudness on the first note, on the fundamental tone, but for the other tones, for the overtones, those are not going to be the same. So you'll see very soon, right? So the first tone, same loudness. Second tone, the first overtone, I should say, second harmonic is 40 on the flute, but over here it's going to be 0. Okay, and then it's the opposite for the last overtone. Right here it's going to be 0, and over on the clarinet it's going to be something like let's say 30. So that's how a synthesizer fakes sounding like all these different instruments. And I'm just gonna fix the order of things so it looks a little nicer, like this. Okay, cool. Yeah, nice. Okay, so you can see this is kind of the way you do synthesis using a machine, right? The machine just has a bunch of numbers. It tells you where are the overtones for this given instrument and how loud should we play each of them so it sounds like the original instrument. And that's like the bare bones of how a synthesizer works. There's actually a lot more to it. Later, this is something I do care about for this project. We'll have to deal with things like the envelope, the attack, and the decay. Yeah, lots of extra things to worry about. But for now, this is the basic picture of how you can synthesize music and different sounds. In fact, any sound you care about, you can synthesize with lots of these tone generators at different frequencies, at the different overtones, and also controlling the loudness so they mimic the overtones of the thing you're trying to copy, right? So that's the basic idea of the synthesizer. And let's see, if you're here for the when I did the Leonard Cohen deepfake project, I had a whole bunch of these spectrograms which show this kind of effect visually, graphically, right? So let's go aside spectrogram. So a spectrogram is just like a picture of sound in frequency space. So what that means is normally sound is this wave, right? But instead of doing the wave thing, we could actually just draw out the frequencies in terms of their intensities and plot them like a plot, really. And so I'm gonna try pulling up one of those pictures to help this explanation. Let's see. See, the problem is I don't remember where I stuck these things. Okay, it would have been under Cohen project, deep learning, outputs, converted. Nope. I do have them somewhere. Okay, I give up. I will just look up a spectrograph. Spectrogram. Yeah, so these are some nice pictures like this, right? This is a pretty typical look of a spectrogram, although it's really zoomed out, so you can't really see any details. And you can tell because everything's really like, it looks the same. So that's why, like, this is a little better, right? So this is pretty obviously a sound. So let's just copy that on. Yeah, so let's kind of dissect this image a bit. So like I said, this is just like a graph of the sound. And on the x-axis is the time, as is usual. And on the y-axis we have the frequencies. And of course there's one hidden axis here, which is the intensity of the sound, and that's the colors you see, right? So let's label our axes. Here we have frequency at the bottom. We have time. And of course, the most important thing, which is the thing that controls how loud your synth plays. That is the intensity. So we're gonna draw that up here. Okay, so that's our picture. There's like 3 dimensions we have to worry about here, right? We have to control time, frequency, and then intensity. Today, we're not going to get too complicated. I'm mostly going to care about the intensity and some of the frequency information, and I'm going to kind of let time sort itself out. Basically, we're not going to worry too much about that today. Okay, so you might ask, how do you get these lovely pictures? Right? Because they are very convenient and they're much easier to understand than these waves, right? So the answer is we have to kind of go back in time quite a bit, actually. And in fact, we have to go to Fourier. So this guy, yeah, wow, he looks like pretty well fed here in this picture. So Mr. Fourier was a mathematician, and he was working on a really important problem of the time, which was called heat conduction. And you might be really confused at this point, like, what does heat conduction have to do? Wow, he lived in like the 1700s, right, to 1800s, so like over 200 years ago. Wow. You know, imagine this stuff was invented 200 years ago, right? So the point is, Mr. Fourier was working on heat conduction. And the thing you have to know about heat conduction is the rate at which heat transfers depends on how hot something is. So what we can say is it's a little more complicated than that. It's the rate of the rate. So in math, we call this the second derivative, right? So how would I describe this? The acceleration of heat. So you could say that heat is man, this is really hard to describe without using math terms. But anyway, the point is that this equation requires second derivatives. Now, the other thing that requires second derivatives is waves. So turns out after he solved this heat equation using Fourier transforms, which are just magical beings, turns out you can apply the Fourier transforms to sound and any kind of waves as well, and you'll get the same effect. So what does the Fourier transform do? Well, basically it does this, right? You can take any kind of equation that looks like, let's draw a squiggle. I'll see how much of my Fourier transform class I remember from undergrad, which is not much, by the way. So here's your squiggle, some kind of sound, right? Or any wave, doesn't matter what wave it is, okay? And what Fourier said is that you can take this wave and you can break it into pieces. And the way you do this is pretty darn ingenious. So I'm gonna size it down a bit because I'm gonna need some space. The main thing he proved, which was kind of the point of the Fourier theorem, is that you can actually approximate this little squiggle exactly with a whole bunch of sine and cosine waves. So if you don't know what those are, let's draw a sine wave. A sine wave is just like a really neat little waves like this. And the cosine wave is like that. So the idea is the sine and cosine waves are like the elementary building blocks of waves, and they look like this. So one is going to be blue, the other is going to be orange, right? So these two are our fundamental waves. And so what Fourier found out was that you can combine these just by like stretching and squeezing them. So you can stretch them this way, which is the amplitude of the wave. So you can think of that as how loud the sound is. And you can also squeeze them this way, which is changing the frequency, if you recall, right? And basically, by doing these two operations and adding up a whole bunch of these waves, you can approximate this wave down here. In fact, you can do better than approximate. If you add enough waves in the limit, you will get exactly this wave back. And the way he did it was quite ingenious. Basically, he found it doesn't need to repeat. You can have any arbitrary shape down here. And what you do is, so long as it's bounded on two ends, you can just make infinite copies of it, like this, right? And you can just like copy it forever. Right? And once you have infinite copies of this thing, then you fit these waves onto it. And turns out that by fitting these waves onto it, you will get a exact replica of this infinite copy, except where the copies join up. So it's possible that at this join you get the wrong number, but everywhere else, like inside the middle of this wave, you'll get exactly this result out, which is kind of amazing. In fact, there's kind of a functional analysis way of thinking about this, which is like sorry, that's out of phase. There's a functional analysis way of thinking about this, which is that the sine and cosine waves form a basis over the infinite vector dimensionality of functions, which is even more amazing. So I'm not going to talk more about that, but the point is that you can get any wave by adding up these fundamental waves. Well, guess what else is a fundamental wave? Well, our overtones, right? These are each a sine wave in this case. And so the Fourier allows us to use his Fourier transform to go from arbitrary squiggle down here to these nice overtones and kind of count up how much energy you need for each of these overtones in order to recover this funny squiggle on top. So let's draw a big fat arrow. This is what we're doing. Yeah. All right. And we'll make it red because this is a cool result. All right, so that is the Fourier transform. Okay, so what that lets us do is once you apply the Fourier transform, you can kind of create a chart. So let's create a chart here. We'll say like frequency. We'll say like 80 hertz. And then like 100 hertz, and then like 120 hertz. Right? You know, we'll just do a couple as an example. Okay, 140 hertz. Well, I cannot spell. So at each of these frequencies, we're going to have some kind of amount of energy. So let's say there's 0 here, 20 here. I mean, ignore the units. These units of loudness are arbitrary. Let's say you have 15 here, and 10. Or let's have some random numbers in here. 8. Okay, so what does that look like? Well, you can imagine here's your 80 hertz wave, right? It's really wide, but it's got 0 on the amplitude, so we have to squeeze it all the way down like this. Right? So there's our 80 hertz wave, and then at 100 hertz, it's less wide, but it's taller. Right? It's actually quite tall. It's like 20. According to our loudness, and then like we gotta squeeze it down a bit, right? 120, that's like a little less and a little shorter, and then finally 140, that's gonna be like even less and quite a bit shorter. So if you add up all these waves, you recover the thing you want. That's the basic idea behind the Fourier transform. Now, we're missing actually one thing here, which is the phase information. So if you recall, I said you can decompose this squiggle into sine and cosine waves. We're missing one of those, right? We only have sine waves or cosine waves in this case. So there's actually another set of numbers just like this, which correspond to the cosine waves. So let's just copy out the whole thing and move it down. Except we'll just shift it over a bit and give it the cosine look. Yeah, so you can see this is kind of what it actually looks like. You have two kinds of waves for every frequency bin, and they all like sum up to this squiggle. Actually, now that I think about it, you don't need all of these bins because it's like you only need like every doubling. So it would be more like 80 and then like 160. Yeah, I don't. That's too much work to edit. So I'm just gonna delete that. Okay, that's better. 320 and 640, so forth. Right. Yeah, I forget which result it was that shows you don't need every possible frequency bin. You can do a continuous Fourier transform, but the discrete one is also capable of arbitrarily recovering your funky looking squiggle. So that's the idea behind the Fourier transform. And this is why the heat equation actually has something to do with sound. If you're curious to hear more or read more about this, just look up differential equations. Actually, don't do that. Differential equations are not fun to study. But yeah, this is a second order differential equation that we're solving. And yeah, heat and sound are related. So now where are we on the menu? We talked about overtones, we talked about synths, we talked about the heat equation, fast Fourier transform. Okay, so the basic idea behind this is since the olden days of the 1800s, we invented computers. So why does this matter? Well, if we go back to the Fourier transform, and this is something that confused me for a long time until I actually studied it. I thought, okay, the Fourier transform only works for like repeating signals, right? Like it can't possibly work for any arbitrary function. Well, the answer is no, it works for any arbitrary function. And then you might be wondering, okay, if I have this squiggle that like starts like really squiggly, but then on this end, let's say it stops being squiggly, it goes straight like this. Oops, not like that, like this. Okay. So let's say I have this function instead, right? Well, it's pretty clear if I try to fit a Fourier transform to this, let's say it squiggles at the beginning, then it's flat forever. Like for a very long time, I should say, not for forever, because the Fourier transform won't fit this end otherwise. But if it's really flat on this end for a long time, then you're going to get a Fourier transform that matches that. So you'll have a lot of silence over here, and then a big squiggle on this end. So how can you possibly approximate music which is doing things at different amounts of time, right? So let's say this squiggle only happens once, but now later you have a sound where the squiggle happens like a lot. So I'm just gonna copy it out like this, right? So you can see that these two things will have two different Fourier transforms, and that's totally fine. That's how the theorem works, right? That's how the transform works. But it doesn't really help us when we're trying to do music synth. And that's because like obviously these two things are gonna have different outcomes on this frequency graph, right? They're gonna require different frequencies. So how can you actually approximate any arbitrary sound with like these frequencies? Well, the answer is the fast Fourier transform, and it's not fast in the sense that it's well, it is fast, but like that's really not the reason why it matters. Actually, the technical reason is it's the discrete Fourier transform. Have different. So the solution is discrete. Okay, so the idea here is that music is changing all the time. And what we want to do in a signal processing context is we want to be able to like capture what the music sounds like at any given moment. And sometimes the bass is playing, sometimes it's not. Sometimes you have the singer singing, sometimes they're not. Sometimes the kick drum's hitting, right? And so what we're going to do is we're going to chop up time into tiny chunks. So let's do that. Let's use a square to chop things up. So we're going to have a window like this. Okay, so here's our window. We're going to make it really thick. Yeah. Thick window. Okay, so we start at the beginning. We're gonna chop up this music, and then we're gonna move the window over, chop that out, and move the window over, chop that out, and so forth. You get the idea. So now if we look at each window, suddenly everything's different. If we do the Fourier transform just on this window, like just this sound, nothing else, you're gonna get one set of waves. And you'll notice now that it's the same in both windows, right? Because they're both on the same waveform here. You move over one, you get a new window. You have the same wave here. So that's totally fine. Same wave. Now here it's different, right? So on the top, now you're just gonna have no sine waves going, right? Because this is silent. But down here, it's the same as the first window. So you're gonna have the same set of frequencies as the first window. So that's the whole secret behind the discrete Fourier transform. And the reason why we can do it really fast is because computers. And that's what allows us to chop up sound into all these tiny little sound bites and end up with a Fourier transform for each one. So what you're seeing up here on this spectrogram, let's bring it down here. Spectrogram. So what this does is we can take this and plot it out, right? So each window is one of these vertical slices here, and then the horizontal part, right? The columns, sorry, the rows of that vertical slice tell you how much energy is in each frequency of this Fourier transform. Let's add in a little label, Windows. Chop up sound into okay. Nice. Oh, that's way too wide. Okay. Nice. That's better. Okay, so let's see where we are along our kind of recipe here. We've gone overtones, we've gone synths, heat equation, fast Fourier transform. Okay, we're almost done. So once you have this, right, the whole idea behind synthesizing music is you just need to match up your sine waves to the frequencies you see in this picture. And then in theory, you should have something that sounds pretty similar. Right? And in practice, the way that talking piano works is instead of having a computer or a machine generate these fundamental frequencies, you're just going to have the piano generate them instead, as in you're actually going to play the piano for each of these frequencies here, and you're going to play them according to how loud they are on this frequency chart. Right? So that's the basic idea behind using the piano to synthesize or emulate another instrument. And I think the most fun way to do this is to try to emulate someone talking, because when somebody talks, so the way we end up making different sounding vowels when we talk is we change the shape of our mouth. And it's like we have an instrument here, which is our vocal folds generating the sound, and then it goes into our throat and our nose and our mouth, and the shape of those actually controls which of these overtones that are coming from our vocal folds are amplified or reduced. So we're actually a walking synth box, basically, right? So we are this here in some way. So the idea is that when you say something like ah, you see you have to open your mouth to do that, and that's because ah has a lot of overtones in it, and the open mouth allows those overtones to ring out. Now if I say ooh instead, you see I have to really close my lips to do that, right? I have to go ooh. I can't go you can't make an ooh sound without closing your lips, and that's because the ooh sound actually has less of the certain overtones. I think it's the high ones. They can't, basically they're impeded. Like, remember the clarinet thing, right? Small opening creates a high impedance, and so it suppresses some of these overtones. They can't get out, basically, and so they sound less loud compared to other overtones. And so that's how you can actually tell the difference between an ah and an ooh. And if you look at it in the spectrogram, which hopefully we'll do today or next week, you'll actually see the difference in overtones. So the way the talking piano does this is it just tries to copy so we just need to control two things, which is which frequencies we play the notes, and also the how loud we play each note. And the closer we can get that to the original spectrogram, the closer we'll get to emulating or synthesizing a voice. So that's the idea. And now that we've covered all that theory, it's time to get some code. And so today I'm not going to try writing anything. I'm actually just going to see if I can get somebody else's code running as a baseline. And then next week we'll do some more like more work to try to make things a little more sophisticated than this. And I've got reasons for that, believe me. So let's see. I've got this resource here. Thank GitHub for their contribution to science. So here is somebody's code. I hope there's no bad words or anything in their code base because I'm going to show it on screen. So somebody did this. Let's take. Oops, that is their home. I just want to look at their repo. So it says it was a hack. They submitted. They won a. Oh, awesome! They won an award. Yeah, and it should be able to generate this piano music that sounds like somebody talking. And the important part is this. And so we don't care about the web interface. We're going to mess around with the code directly. It says you can clone the repo, pip install requirements, and then start the web app, or you can run process audio, wave to MIDI, and then you can generate the MIDI. Awesome. Okay, so this is why I wanted to do the 12-tone project first, because I already had to do MIDI there. And you can see this thing generates MIDI. So that's the easiest way to create some piano playback. Okay, so let's do it. I'm gonna copy their code. So first thing to do, clone it via Git. Let's pull up our VS Code. Okay, I need a new folder. So wait, I'm on PowerShell. I want to be on Ubuntu. Can I open remote WSL window? Okay. So what that does is it gets me onto my Windows subsystem for Linux. Okay, so now I can run Linux commands like this. First thing we're going to do is create a new directory. We'll call this singing piano. Jump into it, and we're going to yeah, let's clone it directly here. So git clone this. Okay, that's pretty quick. So once we have their code copied, I'm going to take a look into it, and the question is, what exactly do they need as a requirement? Do I trust the authors? Yes. I hope they don't have any nefarious code. Otherwise, we're not going to be in for a good time. Did I not finish cloning? Apparently I did not. Okay. Let's try that again. Okay, so while that's cloning, I guess I should pick out something that I want to make sound. Oh, it's done. Okay, never mind. I'll get back to that later. So it requires CherryPy, FFmpeg, that's a sound library, I think. Librosa, okay, that one's important because that's how you can generate spectrograms. I've used it before. It's a Python audio manipulation library. Matplotlib for plotting. Music21 I haven't heard of. OpenCV is the computer vision. Why would they need OpenCV? That's interesting. Okay, I don't know what Music21 is, so let's find out. So according to this, Music21 is a toolkit for computer-aided musicology. So, oh, that would have been handy for our 12-tone project. You can do 12-tone stuff. Looks like it does generate kind of random things. So I'm just gonna look up where these are actually in the audio. So it looks like process audio requires it. Music21. Of course, I don't have it installed, so that's going to be a problem. I'm guessing some of these things are Music21 objects. Okay. What else did they have? So they have website assets. We don't care about those. Okay. Some kind of script file, shell script. MuseScore. Okay, these are import ones. This calls MuseScore. So MuseScore is that notation program I was using. We probably don't need that because I don't need a score. I just want the MIDI. I just want to play the MIDI, right? Options. So this is some kind of some kind of configuration file for generating things. Don't care really. Process audio. This is where the magic happens. So I think this is the most important thing. You can see Librosa is here. Music 21 is here. What else did they require? Cherry Pie. What is Cherry Pie? Oh, it's a web app. Okay, so we don't need Cherry Pie. In fact, I'm gonna remove this from requirements. Librosa, okay. And where do they use OpenCV? That's what I want to know. OpenCV is not used anywhere. Oh, that's because it's not called OpenCV. This is one of those tricks. It's called CV2 for some reason. Makes no sense, but that's how it is. It's called Visualize MIDI. Okay, interesting. Do we care about visualizing MIDI? I don't think so, but okay, I'll leave it for now. Okay, we don't care about the web app, but we do care about this. Okay, so let's get this these requirements installed, and for that, I'm going to create a new environment. So cd. Actually, let me see if where do I store my infs? Here. Okay. So you know what? I'm gonna change things. No, I like keeping the environment separate because then it doesn't show up when I'm trying to do development. So let's create a new environment. Virtual env Python 3, but we're going to call it singing piano. Okay. And now we're going to source activate it. Okay. And then now we can pip install everything we care about. So let's do that. Pip install upgrade first. The installer upgrades itself. And then everything, we want everything in the requirements file. Oh, it's not here. It's in requirements. Okay, so now we sit back and relax. This is one of those things I really like about Linux over Windows is you can just hit a command and it'll just install everything you need. It's like there's no messing around with finding a website, downloading the exe or MSI, and then you have to open it up, right click on it, and sometimes you got to do some other things. It's like, oh, and then there's like version control issues. There's also version control issues in Linux, but you know, it's just like it feels better somehow. Okay, something went wrong though, so maybe it doesn't feel better. It failed building MIDI. Why did it fail? Failed to build MIDI. Okay, which thing is it? Yeah, so there's a MIDI package, and it failed the MIDI package. Interesting. Where does it need the MIDI package? Okay, something generates MIDI. Librosa makes stream. Right, stream. Where are these from? Interesting. Make note. I wonder where these are from. I wonder if they're from Music 21. That's what I wonder. Let's use the environment first. Python select interpreter. /env. We need singing piano. I did find it, right? Okay, it's doing that thing again. Oh, there we go. Okay, it just wasn't entering. Okay, there we go. So there's no MyPy, that's fine. Okay, actually I'm gonna install MyPy. Okay, let's make sure we have everything. Let's see what we have. MyPy extensions, typing. That is not a lot. What happened to MIDI? That is sure interesting. Yeah, I didn't install it. Okay. Let's see. Did I really not install librosa? I mean, I collected it. Okay. So it's trying to run, and then it fails when it's trying to install MIDI. And it looks like there's an issue with... I wonder if it's too old. That's kind of a problem, isn't it? I wonder if it's only for like Python 2 or something. Well, so much for the plan of just stealing some code and making it work. I'm going to install each thing independently so that I can figure out which thing is failing. All right, so let's start with librosa. See if that works. Looks like that's fine. Okay, so if we can get away without using ffmpeg, maybe we will be okay. It depends on what's breaking, of course. So we'll just install each thing one at a time, and then eventually we'll hit something that breaks. And then that's the thing we gotta avoid. Okay, that's fine. So it looks like the issue is with ffmpeg Python. And we're going to try installing it, and then if it breaks, gonna have to live without. Okay, so that was fine. So maybe it was OpenCV. That's interesting. Oh, there's also this. Whatever that is. Python MIDI. Interesting. Okay. Where's it used? That's the question, isn't it? Import MIDI, that's where it's being used. Okay, so the good news is I was just working with Mido last 2 weeks. So we could just replace all the MIDI stuff with the stuff I was working on, and that should be fine. Okay, and where is it using CV2? Oh, for visualize MIDI, of course. So remember, we only care about process audio. So is there any MIDI stuff here? I don't think so. Okay, so I think we can just run process audio and that'll be fine. Okay, now let's check the README and see how we do that. It says to run our code programmatically, process audio. Import process audio, then run wave to MIDI. So let's look at wave to MIDI. Here it is, data sample rate. So this is reading some kind of audio file, right? You can tell because there's a sample rate here. And then we have generate MIDI. Okay, so it's gonna run generate MIDI. Let's jump there. Here's the Fourier transform I was talking about, right? STFT, short time Fourier transform from librosa. So that gives you your spectrogram. And then you have amplitude to decibels. So I think that's just converting the spectrogram to some kind of nice normalized volume. You plot the dB, you compute the top frequencies. So I'm guessing what happens here is you look for the peaks on the spectrogram. So basically, if you slice the spectrogram vertically, in fact, I should draw this out. Yeah, okay. So let me explain what's going on here. If we take a cut of the spectrogram like this, I'm gonna make this bright orange. Right here, right? If you take a cut like that, it's going to look in profile kind of like this. Wow, that's kind of ugly, but we'll work with it. So if I cut this profile through, and you can imagine like that the height of this little wave. Actually, I'll turn it sideways so it's a little easier to understand. Okay, so imagine this is the orange line, but I just rotated it 90 degrees. And now the height of this wave tells you how much energy is in that frequency. Right? So remember, we're trying to make the piano copy this. So what we want is to kind of figure out where all the humps of this wave are. And then we're going to make the piano play notes at those humps. So that's going to look like this, right? So in this case, you can see there's a peak here, and maybe a peak here. So those are the places you're actually going to ask the piano to play notes. And so that's what we are doing here, I'm guessing, top frequencies. And then the last thing is to turn this into some kind of a music. So actually, sorry, I gotta be right back. So give me one moment. Okay, so that was my hour warning. So I think I've got maybe a little less than an hour left before I have to close off the stream early tonight. Hello, cat. The cat is here. Say hi. Say hi to the world. Okay, so hopefully we can get this running before the stream ends, and then next week we'll start coding. So let's see. Jumping back into things, we were trying to analyze the code to figure out what's going on. We've got generate MIDI here. Okay, we got to compute frequencies, and then there's something called make stream from the top frequencies. This looks like the MIDI generation, so let's look here. Yeah, that definitely looks like make stream. Okay, cool. And there's a make note. I have no idea where this is from. Note. There's a music 21 package. Okay, cool. So the notes are from there, and then once it creates that stream, I think let's go backwards. Make stream was called in generate MIDI. Then you write the stream to the file, and then you're done in theory. Okay, let's try running it. So going backwards, back to where that came from, wave to MIDI is what we need to run. So let's do that. For that, I'm going to need some kind of sound file as an input. Right, so let's create a sound file. Actually, we have some sound files from the Leonard Cohen project. I'm just gonna pull some Leonard Cohen's sultry voice down, and we'll try to turn that into the piano. Okay, so give me one moment to find the Leonard Cohen recordings. Cohen project. And deep learning examples. No, that's not what I want. I need the data. Where's the data? Wave. Okay, cool. Waves. And hopefully there's no copyright strikes incoming for me playing copyrighted stuff. I'll play a really short clip. That'll keep it from being a problem. Wow, those are really long clips. Okay, I'm gonna need Audacity to clip them. Skip. Cool. Train A. Okay, I've got lots of short clips here. This is better. Yeah, okay. Sorry. So originally I thought maybe I have to clip something, but turns out I have something like this. Okay.
If you are the dealer.
Oh yeah, that's nice and short. Cool. Okay, so that's Leonard Cohen's lovely voice from, this is from his second last album, You Want It Darker. This song won awards, by the way. Anyway, we are going to turn that into the piano saying that. So let's copy it into our Linux thing. And I'm going to create a thing called Wave. Okay, so you can see I just created a folder called Wave. Here is my audio. Okay, so what we need to do is run Wave to MIDI after importing process audio. So let's try that. I'm just going to use the Python interpreter. So Python import process. Oh, right, I'm in the wrong directory. So I'm actually going to change directory into the directory with the code that I just downloaded. Run Python from Python from here and import process audio. Okay, apparently I can't import it. Why? It is called process audio, right? Yes, it is. It's under source, that's why. Okay, so the problem is Python's looking for, there's like a default path that Python looks around for this stuff. It's under source. Okay, there we go. Yeah, so we've got the module. Next, what do we need to do? We need to run process audio.wave to MIDI. Cool. And it's going to have this look. We have input.wave, output.mid, and then some other information. Do we need that information? Params. Looks like we do. Okay, so I'm just going to copy their command exactly and then edit the input and output. So we'll call this output wave or output.mid, but the input is going to be, we need to go back out a directory because we are here currently. And we need to go out and into wave. And then we need this wave file, which is darker1. Okay. Okay, we're going to leave everything else the same and hopefully it works. Actually, I'm going to move the output to like out. So we're going to need a new directory. Cool. Out. Okay, let's see. There was some kind of error. Audio data must be of type ND array. Okay, so we need a NumPy array. The question is, who needs the NumPy array? It says it was at generate MIDI when it ran the Fourier transform, looks like. And then it jumps into the librosa code here. So what it's expecting here is data needs to be a NumPy array, but it's not. Okay, so why is that? Let's see. It generates MIDI. We're just going to walk through it in our head because I don't know how to use a debugger apparently. But okay, so you can see it's pretty obvious what happened here. MIDI, generate MIDI here. Oh, okay, sorry. Data comes from read. So we need to figure out what happens here with read. Okay, so this is a library called sound file. Okay, what does read do? It should provide data from a sound file as a NumPy array. Right, so the file should be the first argument, which it is here. Right. Okay, so the question is, why isn't this data thing a NumPy array? Okay, the easiest way to find out that I know of is to do some print debugging. So we're just gonna add a print statement here. And unfortunately, we can't just keep debugging through here because we can't change the code. It's already been imported here, right? Now, so I'm actually gonna exit here and instead I'm going to make a little script to do this thing. So let's create a script. We'll create it inside their directory actually. We'll call it wave to MIDI. Yeah, well, we'll keep it in Python. So it will be, should I keep it in Python? Yeah, okay. Import from source, import process audio, and then we're gonna do exactly the command we ran earlier, which was, apparently it's gone. No, it's here. Here, okay. Cool. So this is just convenience, right? I just don't want to be typing this out again and again. We'll just run this instead. So now we could do something like Python wave to MIDI.py, and it should run and cause the same error, which it does. Okay, now though we have a print statement. So you can see it printed something because I added a print statement here, print data, and it looks like it's just some kind of yeah, that looks like an array. In fact, if I print the type of data and I run this again, yeah, wait, that is a NumPy array. So why is it complaining? Audio data must be of type ND array, but that is an ND array. So it must be something else which is causing the problem. Data.t is 0. That seems a little bit suspicious. So let's see what's going on there. Okay, so the type here is fine. We're going to jump into generate MIDI and take a look. So right now it's printing the parameters. I want to know what the type of data T0 is, because that's where it's complaining. And we'll just print it out as well. Okay. Sorry, let's do it again. Okay, it says it's class numpy.float32. What? Okay, that's definitely the wrong thing, because it was numpy.ndArray, and now it's numpy float32. Looks like what happened here, I know what happened. So data.t gives you the transpose of this matrix, but then 0 gives you the first element in that matrix, and I'm guessing it's expecting a two-dimensional array. Now, why would it expect a two-dimensional array? Well, because a lot of sound is in stereo, so there's two channels of sound. So it's just pulling out the first channel of sound, but there is no first channel. This is mono sound. And I know it's mono because I generated it for the Cohen project, which could only handle mono sound. So I think this is the problem. It's expecting a stereo sound. And then if we look at the shape here, I think we'll know for sure. If I print out data.shape, that tells you what the array dimensions are. Let's see what those are. So you can see numpy float, that's the type. This is the dimensions of the original array, and it's just got a ton of samples in a line like this. It's a one-dimensional array. And so when you transpose it, it becomes the same thing because there's only one dimension. And then it takes the first thing, which is just the float. And we don't want that. We want the whole array here. So the simplest way to fix this is I'm just going to hack it and get rid of this 0 here like that. Okay, but I'm going to do it here because that's where it gets affected. Okay, let's try running this again. Okay, seems to have worked. Let's see, there was a warning, something about amplitude to dB on complex input. Okay, so that's fine. This is, so to explain what is going on here, you have to understand that in practice nowadays, remember that the Fourier transform creates two different waves for every frequency, right? You've got the cosine part and the sine part. Well, the easiest way to represent this, like in math and on a computer, is using complex numbers, so imaginary numbers, right? So you have a real component and an imaginary component, and that works because you can think of imaginary numbers as like the rotation of real numbers by like 90 degrees, right? So which is exactly what a cosine kind of does, right? It's 90 degrees out of phase of the sine wave. So because of that, well, in this case, what we want is not the sine and the cosine as separate waves. We just want like the total amount of energy. So we want to add both of those waves together. So when you call amplitude to dB and you add in, you give it complex information, what it does is it says, well, you're going to lose some information because we're going to squish these two waves together, right? The sine part and the cosine part. And so you do lose information. Specifically, it says phase information. Phase information is basically where in the wave you start. So if I go back, if I go back to this picture, let's draw some phases. Where are my waves at? Here. Okay, so these waves are in different phases, right? So if I match them up like this, that's the same phase. And this is a little out of phase. And if they are completely opposite like this, we say 180 degrees out of phase. And that's because if you keep going the same amount, eventually they match up again, right? So that's 360 degrees. It's like a circle. It goes around. It repeats, right? So there's this deep connection between circles, actually, and sine, cosine functions, and, you know, the imaginary number, Euler's identity. Anyway, the point is that if you go 90 degrees, that's where you get the sine and the cosine wave. Right? That's about 90 degrees. So in this case, we don't care about this information. We don't care about where the wave starts because, like, unlike with a computer, right? Unlike with these electronics, I can't actually control where the waves start and end. When you're playing on a piano, it's like the piano is going to play the wave wherever, right? So you can't match up any of these phases of these waves. So there's no point in trying to model that. We're just going to try modeling the amplitude of the sound. So let's do that. Bring our data back, bring our code back, reset everything. So that warning doesn't matter because that's what we want. Now let's take a look and see if we got some output. We did. That's the MIDI file. And now we just want to play that MIDI file. So I'm just going to open it. Can I open it using the Windows Media Player? Let's find out. Okay. Moment of truth time. Okay, so just as a reference, here's our original sound file. I will turn off the audio. So I've turned off the music. Let's hear that.
If you are the dealer,
yeah,
I'm out of the game.
Yeah, my voice cloning sounded nowhere near as good, but that's the real deal. Okay, now let's take a listen to the output MIDI file now. Okay, I don't think that sounded like anything, but let's hear it again. Okay, I cannot hear for the life of me what that sounds like, so I'm going to turn up my own audio a bit. Yeah, I'm not convinced. I'm not convinced it sounds anything like Leonard Cohen, but let's hear it one more time. Like, it's not even the right length. Hello? That's like, what, 2 seconds? How long was the original?
If you are the dealer, I'm out of the game.
That's like 4 seconds. Yeah. Somehow it decided to only play 2 seconds. What? That is very strange. It might be the timing, actually. It might just be it's mistimed. That happened with the other MIDI, if I remember correctly. Let's see. Yeah, so there is a tempo thing here. Maybe the tempo's screwed up. I wonder if I can play it at like half speed or something. So let's take a look. Output mid. Yeah, it's way too fast. That's part of the problem. Okay, well, let's open up MuseScore and take a look at it. We need to turn off all of these. Okay, and apply. Wow, that's a lot of voices. Yeah, so each of these is an independent thing, right? I wonder what it sounds like. It's probably going to sound even worse, but because the timing is going to be messed up by MuseScore trying to import it. Yeah, so now in this case, it's way too slow, right? You can see this is way longer than 4 seconds, right? Maybe that was not the best example. So let's try recording something maybe a little simpler for this thing. And I'm going to record it slow in case it's getting sped up by the MIDI playback, I'm going to try recording it really slow. So we're going to say something like hello world, and we're going to say it as slow as possible. Okay. Hello world. Hello world. Sorry, that's really like off because it's mono. So I need to change this to mono. It's tracks. Mix stereo down to mono there. Wow, and it's clipping like crazy. Wow, it's really clipping. Okay, I'm going to record it again, but with a little less clipping. Hello world. Maybe even slower than that. Yeah, okay, let's try that even slower. Add new mono track. Hello world. And it recorded to stereo again for some reason. It's probably because my interface is outputting stereo. Oops. That's okay. We can mix down to mono. Tracks, mix. Mix stereo down to mono. Okay, get rid of that. Hello world. Okay, we're gonna see if this funny little clip is able to... Oops, I don't want MP3. I want WAV. So MP3s are compressed. We don't want them compressed because we are going to need the uncompressed file for the program to read. So we'll call this hello world, or just hello. Okay, don't care. Now, let's try taking our hello WAV file and sending it through this talking piano software. And we'll see how that goes. So I just copied it in. Let's give it a run through and bring the lo-fi back. Yeah, all right. You know, I didn't think I'd like lo-fi, but it's kind of growing on me a bit. Okay, so the thing we're running is this, not the web app, not process audio. We have our own little script called wave to MIDI. So that's the thing we want. I'm gonna close up everything else. Okay, so this time we don't have darker one, we have hello. And the output, we'll call this hello as well. And now we can run it. Okay, there's a warning. That's good, it finished running. We have hello.midi here. So now we're going to try opening it up. Hello MIDI. Okay, here goes. We'll see how this works. Okay, I have to turn off the sound again. The music. That's better. I can actually recognize it this time, right? So listen very closely. So you'll notice that it actually does pretty good on the vowels. So for context, here's the sound again. Hello world. Here's the recording of me, right? And then if I play back, you can hear this part when it's saying and o. It's pretty clear that that's correct, right? But when it's trying to say h or world with the right, those consonants, it's not doing so well. Yeah, so you can't hear the D at the end at all, right? So let me try playing the world part again. It sounds like this, because it's missing a lot of the consonant sounds, and that's because those tend to have a lot more high frequency content, and also very brief amounts of high frequency content, and so it's just not appearing. But still, it's a pretty impressive effect that you can just get that from a piano. And I just realized why it didn't work for the Leonard Cohen clip. It's because that was resampled down to like 22 kHz. So if I resample it back, I bet I can make it work. That should not be hard to do. I'm just going to open up Audacity again and turn on the lo-fi. Okay. So we are going to bring in... Oh, we need a new project because I need to change the project rate to 2250. Because that's the rate of this little clip here. Okay, and we are going to, how do you resample? Yeah, you can resample. Okay, so the new sample rate's going to be 44. Okay, so let's see here.
What a dealer.
Okay, so it still works. We're going to export the whole thing. Export as wave. Darker 44 1K. Darker 44K is what I'm going to call it. Okay, cool. Okay, now we're going to try the same deal. We're going to run this guy's code. This friendly fellow's code that I stole. I mean, I took for free. Where is it? Okay, wave. And don't worry, I'm going to write my own code next week because there are some really important things I want to fix with this idea. And this is the difference between a talking piano and a singing piano, which I'm going to be concerned about. But for now, let's run this script first. So we want darker 44K, and we'll call it darker. We'll call it the same thing. Okay, and then run. There it is. I'm just like, I hope I didn't turn up my music too much. It seems a little high now. Okay, that seems more reasonable. Okay, so we have the wave file. Sorry, we have the MIDI file. Yep. So let's bring it back into the land of the Windows. Okay, and now the moment of truth. Here's the original.
If you are the dealer.
I'm not going to play too much of it before I get copyright struck. And now here's the MIDI version. Okay, it's still too fast. It's 44K, right? Yeah, I got the right version here, but it's still too fast. Huh, okay, that's weird. I don't know what's going on then, because I did resample it, right? I'm pretty sure I resampled this. Or did I?
You.
Huh. Okay. Maybe I have to change the, okay.
The dealer.
If I do this. Okay, this is something I'm not familiar with Audacity. I've never actually tried to resample something before. But you know what? It's worth it. I don't have much time left for today anyway. Yeah, I've got like half an hour, so I'm just playing around with this for the rest of today, not much else. So let's do it. Let's figure out how to do resample audio Audacity. I could also do it in FFmpeg, which I've done before. But let's find out. Using our good old buddy Stack Exchange. So it looks like you do have to use the project rate part. Okay, so it says, okay, I know about this drop-down menu, but if you import a file with a certain sample rate's how often the audio file records the volume of the sound, right? So you can think of it as it's just saving where the wave is at every tick. And the ticks have to go really fast because according to the Nyquist theorem for sampling, you need to sample at least double the speed of your fastest frequency, otherwise you won't hear it. Right? Otherwise it actually wraps back on itself. So, so in this case it says the project rate is automatically adjusted if you import something. When you resample the track, the project rate doesn't change, then you need to manually lower. Okay, I see. Cool. So what it's doing when you call resample on this track is probably it's just getting rid of the extra samples if you have too many. Right? So in this case, we're just going to reopen everything just to make sure I've got it. Okay, I'm gonna bring in. Okay, yeah, I gotta wrap up real soon. So now or never. Okay, so yeah, I bring it in. The project rate does change. That's good. So now I need to change the project rate to the correct rate and resample. Cool. And then finally export. Export as wave. And we'll overwrite the previous one. Okay. And last step. Quick. This better work because this is my last go at it. Wave. Replace. Okay. Let's run it. We're still running it on the same file. It's just a different version of it. Okay. It's done. Bring out the MIDI. Replace. Okay. Moment of truth. Okay, it's longer this time. That's good. It still doesn't sound like anything, but I think it's better. It's the right length. So here's the original.
If you are the dealer.
Here's this messed up version. Yeah, so it doesn't sound anything like the voice. At least with Hello World, I could make out the hello. All right. So my guess is that this is a little too low for the piano to reproduce all those like complicated frequencies. So yeah, this is a limitation of this result. And next week, we're going to try to fix it. We're going to try to make things work better. So that's it for today. It's a really short stream because I don't have much time today, but that's okay. Next week is going to go all the way to midnight because it's the due date for the next problem set. So I'm going to stay up. I'm going to stay up basically to see if people have questions. Yeah, so that was fun. Didn't write any code today, but it was nice to just use someone else's bug-free code for a change. So yeah, that's it for today, and see y'all next time.